Hello, so in this video we're going to be looking at stationary points. So let us set the scene. So let me consider this curve here, say like a sort of cubic curve, right? And a few videos ago we saw that it's increasing and decreasing functions, and increasing means the curve is going up, and decreasing means where the curve is going down. And so we saw that if I highlight in yellow the increasing parts, it increases here up to this point at the top here, and then after that point I'll mark that point, I'll circle it there, this point here, then it goes down, then it decreases until it reaches this bottom point here, right? And then it goes up again, okay? So we saw last time where graphs increase and decrease. And we also saw that we can consider the gradient or the tangent to find where it's increasing or decreasing, right? So if I get rid of this, so it's increasing where the tangent or the gradient of the curve is increasing or positive, right? So, for example, in the yellow parts, we can see here, if we are tangent to the curve at the yellow points, we can see it's a positive gradient, right? The tangent is a positive; it's going up, right? So in the left part, the first yellow region, you can see it's going up, and then it's still going up, right? And even if we move to the other yellow side, it's increasing as well, right? So basically we saw that increasing means that the gradient is positive. On the contrary, the decreasing parts is then when the curve is going down, so the gradient is negative, right? So if I then do a tangent to the red part, you can see the curve is now, the line's going down now, right? But then let's investigate what happens when it reaches these points here that I've circled in black, right? What happens as we move to those points in terms of the gradient, right? So we know when it's increasing, it's positive. The gradient, the line's going up, my tangent. But as we move closer, so let's say I'm a tangent here at the curve, right? Tangent here. But then as I'm moving closer to this point, to this point here, what's going to happen is the line's going to be less steep, right? So, and then I'm there, right? And then as I get closer to my point, it's getting less and less steep, right? There's less of a rise, and then eventually, when I'm tangent to that point, it's completely flat, right? And there we are. So at the tangent at the point here is completely flat, right? If I draw this, the tangent's completely flat, right? And it's the same story for this second one here. If I then move my line to be tangent at this point, it's again completely flat, right? So what's happening is, if I draw a bunch of tangents again, if I'm starting from the first point, of the first part of the curve when it's increasing, okay, so we have a tangent here, so we have a tangent there, obviously that's going up, right, increasing. Then as we edge towards that point, right, that I've circled and marked, then that's my new tangent. As I'm moving closer to my point here, as you can see, the lines are getting it's getting less and less steep, right? If you can see my markings, and eventually, if I get rid of all this, we get a completely flat tangent line, okay? And it's the same story here as well. Now that's what we'll be focusing on in this section, okay? A very important type of point. So that particular point then is where the curve isn't increasing or decreasing, right? So the gradient is 0, right? Because it's completely flat. There's no gradient at these points. And what you can notice as well, it's very similar to when we did quadratics, right? With a quadratic curve, we saw it had a turning point, which is at the bottom, or a maximum point at the top here. It's kind of where the graph turns. It goes up and down, or down and up, right? It's the same story here. This is a turning point, and that's a turning point, right? That's what we will kind of be looking at, right? These special points, the turning points, actually when the gradient is 0. Well, what do we know about gradients? We can differentiate, right? So we can apply what we've learned to find these points. So in particular, these are called stationary points. Stationary points are points where the gradient is 0. But we also know that, in other words, if we differentiate, say if we found dy dx, we'd have to set that equal to 0. Okay, and that's how we can find stationary points, by differentiating and then setting it to 0. Okay, and yeah, so that's essentially a stationary point. Okay, now there's obviously a bit more to this. Stationary points. There are 3 types of stationary points, which we will be examining. The first one is a minima, or a minimum, I should say, a minimum, a maximum, and something called a point of inflection. Right? So, if we differentiate it and we get 0, or in other words, the gradient at this point is 0, it's either a minimum point, a maximum point, or a point of inflection. Well, what exactly do we mean by these 3 things? Right, let's have a look at this diagram here. So we've got a different curve, and it's been labelled with all these 3 type of stationary points. So up here is a maximum, okay? Up down here is a minimum, right? And here in the middle, where it starts to level off, is a point of inflection. Now these are all stationary points again. If I get my ruler out, the gradients at these points will be 0. Okay. Okay, flat. Okay, so at point A, you can see it's a tangent. It touches the curve at the point A. It's a flat line. The gradient is 0, so it's a stationary point. At the point at O, you can see it will touch again my tangent line, which is flat. So the gradient is 0 there as well. And the gradient at B, if I go down, is also 0. The gradient 0. So they're all stationary points, but they're all different types. So this is a maximum, and a maximum and minimum shouldn't be too difficult, because really it kind of says what it does on the tin. A maximum is kind of like the top point around the area, right? So it's a top point, okay? So that's a maximum point, where it's the top point in the area. A minimum point, again, it kind of says what it says. It's the lowest point, or the lowest value in that area, right? Now you will also see something called it's described as local. Okay, again, that's the idea, because it's the maximum point in its vicinity, in its area, right? Because obviously this is the maximum area, this is the maximum value, or the maximum point, but actually the curve is going up to infinity up here, right? So actually point A, would it be the maximum value? It would actually be infinity. But in the area, in the vicinity of that area, it is a local maximum. Okay, same story with point B. It's technically a local minimum, because it's the minimum point in the area, not the entire minimum value. Sometimes it will be, sometimes, but as you can see, if we go if you look at this part of the curve, it goes down to negative infinity. So obviously B wouldn't be the lowest value here, but in the area it is. Okay, so these special type of points, stationary points, we can see if it's a maximum or minimum. Now this point of inflection, this other type of point is here, and we kind of looked at that when we looked at sketching cubics. We said if we sketched a cubic, if it's for example, let's say we have x minus 1 cubed, right? If we were to sketch this, it has a triple repeated root. So a triple root. We said that when we sketch these cubics or quartics, we look at the how much a factor or a root repeats, obviously by looking at the factor number. So if the factor or the root repeats 3 times, it's a triple root. And we saw that basically that means, well, x will be 1 is the solution, and it creates a point of inflection, meaning it kind of levels off, right? And then it shoots back up in this way. So as we go towards point 1, it kind of levels off, and then it shoots back up, right? So 1 will be about there, right? So it's this leveling off that gives us, that is a point of inflection, okay? And you can see that here. So as we go down, then it levels off to the origin, and then it goes back down, okay? And so that's a point of inflection. There is another type of point of inflection which we won't be looking at in year 1. We will be looking at in year 2. Something like this. Okay. So a point of inflection would be in the middle. So a point of inflection either levels off like this, or it's between a maximum and a minimum, right? It's in between, okay? Now obviously with this the gradient at the point of inflection isn't 0, right? The gradient is not that, it's not 0. So we will be looking at that type of inflection point in year 2 with regards to concavity, which we'll look at in year 2. But for this part of the course, we will be looking at points of inflection where they level off, okay, which we've seen with cubics and stuff like that. And you can see it's a stationary point because the tangent is flat, okay? It's a flat tangent. So okay, so that's the whole idea. So a maximum point is a maximum point, right? It's the top point in there in its area, and a minimum is the lowest point, and a point of inflection is kind of leveling off, right? In that way. Okay, so we should know what they kind of look like then, these 3 points. So how do we go about finding them then, right? And so we can use gradients to help us work out what stationary point we have. So we can look at the first derivative, which tells me my gradient, right? Okay, so let's consider first our minimum, right? So a minimum point would look something like this. If you think about a quadratic, it looks something like this as a minimum point right there, a lowest point. So this is a minimum, we can see, but let me consider the gradient then. So hopefully you can see, if I look at this graph here, this little simple sketch, it's going down, right? The curve is going down before we get to that point, and then it's 0, and then it's going back up after that point, right? So this is point X, then at the minimum, then we can see the gradient is going down, or it's negative, so the curve is going down and going up, which means the gradient goes from negative to positive. So at a minimum, gradient goes from negative to positive. And yes, so okay, so how can we kind of write this more mathematically? Well, so that means if f dash of x is equal to 0, which is a minimum, so it has, so obviously a minimum point, the derivative has to be 0. And so if it's 0, if it is a minimum, then we can use the sign of the derivative of the gradient, right? By using this idea. So let's say, obviously before, so if we're to the left of the point x, right, to the left of the curve, we can see it's going down, right? So we take the first half of the curve, it's going down. So the gradient has to be negative. So let's say we subtract a very small number. So f dash of, let's say, x take away 0.1, right? 0.01, let's say. Then that has to be negative, right? So let's say if that point is x minus 0.01, right? So let's say that gap is 0.01, right? And so therefore it has to be a decreasing gradient, right? So it has to be negative. On the contrary, if we then add a very small number to x, let's say we have the point here, if we add 0.01 instead, then we're on the increasing part of the curve, so the gradient would be increasing at the point, so it'd be a positive gradient, okay? So that's the idea. We can look for a minimum by considering the sign of the first derivative around the point x, right? So if we're a bit less than x, so if we're a bit less than x, then it has to be negative. If it's a bit more than x, then it has to be positive, because the idea is at a minimum, overall, we're going from a negative to a positive gradient, okay? So that's that then. So we consider the sign of the first derivative. Right, then the next step is maximum, right? The next point. And again, it would look like this. And we're going to consider, again, a very similar argument, right? So let's say that's the point x then. Let's say then let's consider the left part of the curve, the first half. In this case, it's increasing, right? And then it reaches to point x, stationary point is flat, so it's at 0, right? The gradient is positive, and then it's going down, so it'd be a negative gradient, okay? Okay, so we got the signs then, right? So it's going from positive to a negative in this case, so it's flipped. Unlike a minimum where it's going from negative to positive, for maximum it's going from positive to negative, right? If you consider the gradient or where the curve is increasing and decreasing. So at a maximum, gradient goes from positive now to negative. Okay, so again then, in terms of the first derivative, we can consider the sign close to the point x. So if f dash of x is equal to 0, which it has to be because it's a stationary point. So if it's a maximum now, well, let's consider points close to before and after x. So let's say we have the point here, the point here to the left of it, to the left side. That's going to be taking away a number 0.01, right? If we subtract 0.01, right, a very small number away from x, then it has to be positive, right? Because the gradient is positive before the point, as you can see on the graph here. It's a positive gradient, so it has to be greater than 0. On the flip side, if we then consider this point, which is to the right of x, if we add 0.01, let's say, then the gradient, the curve is going down, right? So it has to be a negative gradient at that point. So it has to be less than 0. And you can see that the signs are flipped compared to minimum, okay? So, yes, so we can consider the sign in this case, right? The signs of my function. Now, the third type of function, the third stationary point is a point of inflection, which again looks something like this. So a point of inflection there with that leveling off, like reminiscent to a what's it called, to a cubic curve. So this is a point of inflection. Okay, so we looked at minimum, maximum. Now we've got point of inflection. Now, what's going to happen now is the curve is increasing and increasing again, actually. So it's increasing, then it's flatlined to the gradient of 0. So it's going from positive gradient because the curve is increasing. Then it goes flatlined momentarily at the point. Then it's increasing again, right? So actually what happened, what's at this point quite interesting, it's just constantly positive. The gradient is always increasing, it's always, the curve's going up all the time, despite this stationary point. So it's different to the other 2 points where we're going from negative to a positive or a positive to a negative. In this case, it's just completely positive on either side of the point. So at a point of inflection, gradient remains positive, but actually it could even be negative as well. If I flipped the shape the other way, let's say I instead something like that, right, and make it a bit more accurate. If we then gone the other way, it's decreasing, then we're at the point here where it's flat with gradient 0, which is my point of inflection. Then it's going down again, right? So it's constantly going down, right? So so either way, the gradient kind of remains the same sign, right? So it remains positive or negative. So that means that okay, that means that therefore f dash of x add 0.0 subtract 0.01, right? So either way, if we're to the left or to the right of the point x, right? If we subtract a small number, say 0.01, it would be positive, and if we add the number as well, if we go away from x, right, if we add 0.01, it will remain the same sign, because either side of my point x, right, to the left or to the right, the gradient is the same, right? So it's always positive or always negative, right? But the idea is either side of my derivative has the same sign, okay? So it's always, because of the fact that at a point of inflection, as we discussed, the gradient is always positive or always negative, right? It doesn't change from positive to negative or vice versa, just always positive. There's no change in the sign, okay? That's what I'm getting at. There's no change in sign in my derivative. Whereas in this example with a maximum, change from positive to negative. And for a minimum, the sign change is changed from negative to positive. And that's it, right? So we can use the first derivative by looking at the change in sign. To consider what type of stationary point we have, okay? But obviously mathematicians, they want to find more effective ways of working stuff out. We're not particularly fond of this sort of idea of considering signs. So what we can do instead is consider also the second derivative as well. So we're going to now look at the second derivative, and we're going to look at something called the second derivative test. Okay, so basically we can use the second derivative to do a test, right, to give us a way to show if it's a minimum, maximum or point of inflection in a more easier, more effective, streamlined way. So let me consider then. Let's go back to our example then. So let's go back to discussing our minimum point here, where we discuss that the gradient goes from negative to positive, right? Now, the second derivative is a derivative of the first derivative, if that makes any sense. So, what that means then, if the first derivative is negative to positive, so we're going from negative to positive. If we were to do the rate of change, right? So how much is it? What's changing, right? Because the second derivative is a derivative of the first derivative, so it's all about how the first derivative is changing. Okay, this is the first derivative. We saw that for minimum, it's from negative to positive, right? Now, with the second derivative, then what would that mean? Is basically well, it's going from negative to positive, right? So that means that at the point, if it's going from negative to positive, overall it's increasing, right? The derivative is increasing because we're starting from negative and we're going up to a positive. So you can think of it like this: it's just increasing, right, from a negative to a positive value. Okay. So as a second derivative, then we can say for a minimum that d squared y over dx squared, because it is from negative to positive. Actually, I'll leave that out. Because it's going from a negative to a positive gradient, then that means the second derivative, the change in that, right? So the change from negative to a positive means it's just going up, right? So it's so the second derivative has to be positive, right, at that point. The maximum then is the opposite story. So at this maximum here, we saw that the gradient was going from positive to a negative now. So what's going on? If it's going from a positive number to a negative number, it's going down, right? So if it's going down, then the second derivative has to be negative, okay? And so we can look at the sign of the second derivative, okay, without having to work out around the point, right? So this is my max minimum and my maximum. Now, for my point of inflection, okay, so as we saw with a point of inflection now, with this particular example anyway, the gradient is positive and it keeps being positive, right? It doesn't change. There's no change. It's positive, and then it keeps remaining positive. It remains positive or negative either way at that point of inflection. The curve either continually increases or decreases. Therefore, the gradient remains positive or negative, right? What that means is then there's no change in the values then, really, in the sign. So what we can say is that for a point of inflection, the second derivative, which is the change of the gradient, right, that has to equal 0, because there's no change in the sign of the first derivative, because it's always positive or always negative. There's no change in that. Remember, the gradients are all to do with change, right? So the minimum, we've gone from a negative to a positive, so the changes are positive. So hence, the second derivative is a positive. For a maximum, it's going from a positive to a negative gradient. The change in that is it's going down, it's negative. Hence the negative 0 there. And so a point of inflection has to equal 0. Now, with a point of inflection, this is not sufficient, okay? With these two, if you get the second derivative to be negative or positive, that's great. These two are fine. This one we need to do a bit more checking. We must every point of inflection, the second derivative will equal 0. But then, what we need to do is, furthermore, we need to consider the sign, the sign of the curve, right? No, the sign of the second derivative. So I'm going to say, and there is a change in sign. Okay, cool. And that's it. So the idea is that with a point of inflection, we set the second derivative that equals 0, and then we look at the sign before and nearby the second derivative. So if we add 0.01, take away 0.01, there should be different sign changes. Okay, and that's really it, right? That is really it there. Okay. I should say if we have a point that the second derivative is equal to 0, but it doesn't satisfy, there is no change in sign, right? Then it can't be a point of inflection. It could then be still a minimum or maximum if it's a stationary point. Okay, but we'll leave it there for now. But that's it, right? So actually, we can massively simplify what we just learned by basically looking at this second derivative test here, which our box here. Yeah, so that's essentially what we will be using, okay, to look at these three type of points: a minimum, a maximum, and a point of inflection. Right, okay, so let's have a look at some examples, because this is very abstract without looking at some examples, okay? But this is mainly what we'll be referring to in this case, okay? So, let's have a look at some examples then. We're told, firstly, to find the coordinates of the stationary point on the curve. So, firstly, the curve is y, it's x to the 4, take away 32x. So, the stationary point, you should remember the gradient dy dx has to equal 0, okay? So that's what we're going to do. So if we differentiate this, it would be equal to, well, 4x cubed minus 32. Cool. Okay, and then, so we want the stationary point, which means the derivative has to be 0. That's what a stationary point means, right? So we want to consider basically solving the equation equal to 0, right? If we set the derivative to 0. So we want to consider dy dx equal to 0. So therefore, 4x cubed minus 32 equals 0. And so we need to solve for x then, right? So 4x cubed would be 32. So x cubed would be 8 if we divide by 4. So therefore, if we cube root 8, we get x to be 2. Right? Cool. Now, so that's my x value, but it wants the coordinates. And again, remember, coordinate has an xy part, right? So we need to find the y value as well for the x coordinate. So the y coordinate, well, if we know x is 2, we know the equation of the curve is x to the 4 minus 32x. We can find y by substituting x into that. So y is equal to x to the 4 minus 32x. So at x is 2, y is going to be 2 to the 4 minus 32 lots of 4, which will get me, if I put that in the calculator, minus 48. Oh, that should be 2 there, my apologies. 2 minus 48. Okay. Sorry, when x is 2, y is minus 48. So the coordinate then is x is 2, y is minus 48. Cool, so that's my coordinate, and again, this is a stationary point, as this is when dy dx, the gradient, was set to 0. Okay, cool. Part B of the question says, by considering points on either side of the stationary point, determine whether it's a local maximum, minimum, or point of inflection. So now this is kind of getting at what type of stationary point is it? Obviously we know it's a maximum, minimum, or point of inflection. What point is it? This is where we're going to consider what we looked at the start, and it's said by considering points on either side of the stationary point. What that means is we're going to consider the gradient before and after x is 2. Right, so let's set the scene. So we know that this is my coordinate, my stationary point, which means when x is 2, the gradient is equal to 0, right? Now, if we're considering points around this point 2, so let's consider a bit before and a bit after my point. So let's say we have f dash of 2 take away a very small number, say 0.01, right? And so if we do that, that would get me, and also bear in mind my derivative function is going to be 4x cubed minus 32. That's what I'm substituting this into. So if I substitute 2 minus 0.01, which should be 1.99, into my gradient function, I will get minus 0.47, okay? And that is going to be a negative, okay? And so that's the idea then. We're considering the gradient around our stationary point. So if I set the scene then, let's say I have this situation. Let's say the point 2 is here. That's the stationary point. When we're considering points around the stationary point, I'm considering the gradient around this point. So let's say we have 1.99, and let's say this is 2.01, right? Where we're very close to the point 2, right? We're considering the gradient as we to the left and to the right of my stationary point, okay? So this is the idea, right? So this is 1.99 and the gradient is negative, right? So it's going to go down to the left of the point 2. Now, if we then consider the other way, let's add 0.01, so we're a bit over 2, or to the right of 2. If we put that in a calculator, we would get 0.48, and that would be positive, okay? So now when we're to the right of our stationary point, so when we're at say 2.01 compared to 2, so we're added a bit more than 2. Now the curve is increasing, right? So what's happening is the gradient is changing from negative, right? Negative when it's below 2, so before 2, it's changing from negative to positive, right? And so we have this idea here then, right? If I redraw this a little bit better, so this is my point 2. Let's say this is 1.99. This is say 2.01, right? So I'm a bit either side of my point 2, right? So the gradient to the left of 2, so 1.99, right? My gradient before it is going down, right? That's what this is telling me. But it's when I'm subtracting a bit from 2, the curve is going down. On the contrary, when we're a bit after 2, when we're at the point 2.01, so we're a bit more than 2, then the curve is going up, which is indicated by the positive sign because the gradient is going up, it's increasing. So then there has to be a minimum point then, because if it's going down in this way, then going up, right? If it's going down and going up, it has to be a minimum point. So therefore, the point 248 minus 48 has to be a minimum, a local minimum. Okay, because of this idea here, by the fact that we can consider the gradient around the stationary point, we can use that to determine what our point looks like. Okay, and so yeah, so we can use the first derivative. We can look at the sign change to work out what point we have. Okay. But of course, we got our second derivative test, which is a lot more powerful and more efficient, which I recommend you do whenever you can. And exam questions overwhelmingly expect you to use second derivative because it's a lot easier, a lot nicer. So yes. So in this example, we're told to find the coordinates of the stationary points of this equation. Y is 2x cubed, take away 15x squared, add 24x plus 6. So again, stationary points, the gradient is set to 0. So we need to find the gradient then. So dy dx, if we differentiate, well, 2x cubed would be 6x squared. Take away 15x squared will go to minus 30x. And then 24x goes to 24 and 6 goes to 0. And that's it. Then we need to set it to 0. Okay, so dy dx equals 0 for it to be a stationary point. Therefore, 6x squared, take away 30x, add 24 equals 0. Cool. So this is just a quadratic to solve, right? So xn would be actually I could just yes, I could actually divide everything by 6 to make it nicer if I wanted to. So then x squared take away 5x add 4 equals 0. Okay, cool. And then I can solve, I could probably factorise actually. So I want two numbers at times to get 4, add to get minus 5. So 4 and 1, I could make them both negative, right? Because I multiply to get positive 4 and add to get minus 5. So my factors are x minus 4, x minus 1. So therefore x is 4 or x is 1. And these are my two stationary points. But it says to find the coordinates. Coordinates are x, y. So we need to find the y values as well. So if x is 1, firstly, then y, if I substitute 1 into here, I will get 2 lots of 1 cubed minus 15 lots of 1 squared, add 24 lots of 1 plus 6, I get 17. And then if x is 4, then y, if I substitute 4 into my equation, my curve, I get minus 10. And so therefore my 2 points are x is 1, y is 17, or x is 4, y is minus 10. And those are my two stationary points. Cool. So then part B then says find d squared y dx squared and use it to determine the nature of the stationary points. Very common exam question, that is very common language. The nature means is it a maximum, minimum or point of inflection, and we can use the second derivative test to help us with this. So then if we were to work out in part B, well, the second derivative, well, we already worked out the first derivative, so remember the second derivative is differentiating again. So 6x squared would go to 12x. And then minus 30x will just go to minus 30, and then a 24 goes to 0. And that's my second derivative. Now, I've got these 2 points here, right? These are stationary points. I can use the second derivative to help me determine what type of stationary point that they are. So, firstly, x is 1. I'm going to substitute that into my second derivative. My second derivative is 12x minus 30. That would go to 12 lots of 1 minus 30, which is minus 18. So that's a negative then, right? And then if we go back to our second derivative test, which we discussed at the start, here, a negative second derivative means it has to be a maximum. Now you could, you're probably best to learn it, probably kind of memorize it, or you could maybe understand like how I got there at the start. So you got two choices with this sort of thing. You could memorize the result here, the result, which isn't too bad, but you have to remember the order. If it's negative, then it has to be a maximum. If it's positive, then it has to be a minimum, right? Or you could understand the logic that I was kind of getting at the start of my explanation. But in this question, the maximum, the second derivative was negative. Where was we? The second derivative was negative, so it has to be a maximum. So d squared y dx squared is a local maximum. Okay, then we also need to classify this second point here, 4 minus 10. Oh, no, not d squared. No, sorry, not the derivative. The point 117 is a local maximum. My apologies. Then x is 4 then for this second stationary point. We're going to then do the same thing. I'm going to substitute it into my second derivative to check the sign. If we do that, well, that'll be 12 lots of 4. Take away 30, that'll be 18, and that is now positive. So therefore we can say that 4 minus 10, if it's a positive second derivative, it's a minimum. And so again, you could also understand the logic behind this. Again, that if the second derivative is increasing, remember the second derivative is the change in the gradient. That means the gradient for it the change to be positive, it has to start from negative to a positive, right? So it have to go decreasing then increasing. So it'd be a minimum point that way, right? If it's decreasing then increasing, the change is it's increasing. So hence the second derivative is positive. Okay, so there we are. Okay, cool. Now, that's it, right? So that is the nature of the stationary points. So is it a maximum, a minimum, or point of inflection? That's what it's asking for to determine the nature. Okay. Cool. Okay. Okay. We can also then use stationary points to help with sketching graphs, right? So first of all, we are given the curve has the equation y is 1 over x add 27x cubed. We're firstly asked to find the value of a, right? Well, then we need to, if it's a stationary point, we should consider differentiating it as set to 0, right? Because then dy dx would equal 0 for it to be stationary. So if we differentiate, well, we firstly need to simplify this 1 over x. We need to have it as a power of x. Well, it's a reciprocal, so it'd be x to the minus 1 add 27x cubed. Now, then dy dx then, well, x to the minus 1 will go to minus x minus 2 add 27x cubed. Well, the 3 goes to the front, the power, so 27 times 3 is 81, then x squared. And there we are. Now we need to set this to 0. So then dy dx is 0 for it to be a stationary point. So therefore minus x minus 2 add 81x squared equals 0. Now how do we solve this? Well, firstly it will help to almost convert this back as a fraction. So then we're going to have minus 1 over x squared add 81x squared equals 0. Then we can actually just times by x squared both sides, right? So then minus 1 add 81x to the 4 equals 0. So therefore x to the 4, well, if we move the minus 1 to the front by adding 1 to both sides, we get 1 and then divide by 81. Therefore x then is going to be the 4th root, so plus or minus the 4th root of 1 over 81. Does that simplify? Should do. If we put that in a calculator, yes, we get a third, okay? That would be the same as plus or minus a third. And actually then, x is plus or minus a, we can see that a has to be a third, okay? By just comparing what we've got. Cool. So that's my two stationary points, is plus or minus a third. Now, We're told to sketch the graph from using this of the graph y is 1 over x at 27x cubed. Now we know what individually these graphs look like, 1 over x and x cubed, but adding them together is a bit more complicated. What we can do, in general, with graph sketching, I like to use an acronym to help me, and it's RAILS, okay? And what this stands for is roots, asymptotes, intercept, spell that correctly, intercept, which is the y-intercept, or the x-intercept, but that's roots, right? Anyway, roots, asymptotes, intercept, long term, which basically means infinity, right? So what happens when in the long term the graph goes to infinity and minus infinity, right? Okay, and then stationary points. So when we looked at graph sketching in chapter 4, we could do these 4 things here, but in order to be able to have a full, well, a very good at least idea of what the graph will look like or how it behaves, we also need to consider stationary points, which we can now do, which now allows us to sketch graphs more effectively. So with this idea then, we need to sketch y is 1 over x at 27x cubed. Now, so we're going to use this RAILS idea then. The roots, firstly, we need to check where solving the equation equal to 0, right? So 1 over x at 27x cubed equals x cubed equals 0. So therefore, if we times by x, we get 27. Well, we get 1 add 27x to the 4 equals 0. So then x to the 4 would be negative 1 over 27. Well, hang on, we're going to be rooting this, the 4th root. That cannot happen. If you did the 4th root of this in your calculator, it should get you a wrong answer, right? So that has no solutions. Okay, so because of that, there are actually no roots in this case. So we can sort of tick that off then as we've done it. Then the asymptotes. Now the asymptotes are where the curve isn't defined usually, mainly. So we can see there's an asymptote at x is 0. Okay. So x is 0 is an asymptote. Cool. Okay, so then we are going to look at the intercept. So that's when x is equal to 0. So that's the y-intercept. So then we can do that. So the intercept is going to be well, x would be 0. So then y. Well, actually, there is no y-intercept then, right? Because x cannot be 0, right? Because then you're dividing by 0. Y is undefined. So there is no y-intercept either. Okay, now next we're going to look at the long-term behaviour. So that's what happens when x goes to infinity and minus infinity. Well, let's think about it. Okay, so that's my next ingredient. Well, when x goes to infinity, think about it. 1 over x then, think about like, you can maybe visualise a reciprocal graph, but if you think about it, 1 over x goes to 0, right? But then the problem is here, we're adding x cubed. Effectively, what we're doing is, when x goes to infinity, we're essentially adding 0 add infinity, because x cubed will go to infinity if x goes to infinity. So basically, the whole graph y would go to infinity. Okay. Now, we're also going to consider x is negative, goes to negative infinity. And it's the same argument, right? So if x goes to similar argument. So when x goes to infinity, minus infinity, we're again dividing one by a negative number. So what happens is, this goes to 0 as well. And then x cubed, now think about it, x and x cubed, if x is negative, x cubed is negative, because a negative times another negative would be negative. Meaning, if x is minus infinity, then this x cubed goes to minus infinity. So therefore, overall, 0 minus infinity, you can think of as minus infinity. So that's my behaviour, right? So as x, so in the long run, x, the graph is going to go to infinity, and then to the left, it's going to go to minus infinity. Okay, cool. So I'm going to get rid of this bit now. I'm going to say that y goes to, as x goes to infinity, y goes to infinity, and as x goes to negative infinity, y goes to negative infinity. And then the stationary points, well, we know what the stationary points are, but we don't know what type they are. That will help us as well. So we're going to use the second derivative then. So, we know that dy dx, if I recall, from part A, was minus x minus 2 add 81x squared. So we're going to differentiate again, right? So then d squared y over dx squared, that's going to be plus 2. So minus of minus 2 would be plus 2, x to the minus 3. And then 81 times 2 would be 162. And just x, okay? And that's my second derivative. Now, I have x is a third and x is minus a third, right? So firstly, if x is a third, then my stationary point, that's a stationary point. Then the type, I can look at the second derivative. So if I evaluate the second derivative here, if I plug that into here in my calculator, 2 lots of a third to the power of minus 3, add 162 of a third, I get 108, and that is positive. So therefore it is a local maximum. No, sorry, minimum. Okay, because you need to remember that the second derivative is positive, so it's a minimum. Then, if x is minus a third, then the second derivative here, that's going to equal then, if I plug that into my expression here, 2 times minus a third to the power of minus 3, add 162 of minus a third, I get minus 108. And that would be negative, so it's a local maximum. Okay, so now I know what these points will look like. A minimum is going to something like that, and a maximum is going to look something like that. Okay, so then lastly we need to find the coordinate, right? So if x is a third, then y is going to be, if I plug that into my expression, my curve here, well, 1 over x is 1 over a third. Add 27 of a third cubed, I'll get 4. Okay, so that's the point. So therefore, the point of third, y is 4, is a minimum. And then if x is negative a third, then y would be, if I plug that into my equation, I get negative 4, okay? So therefore, minus a third minus 4 would be a maximum. Okay, and there we are. So now we've worked out all the ingredients to kind of deduce the shape of the curve. So the stationary points are, I'm gonna add that a third and 4 is a maximum. No, minimum, sorry. and minus a third and minus 4, those are the two stationary points, right? That's a maximum. So now we have all the ingredients, right? The key behaviours and the values of the curve. So, okay, I'm gonna, do I have room up here? But, oh, I don't, do I? Okay. Right, I'm gonna get rid of some of this now, to make room for my graph. Because I've already summarised what I've done in my list here, in my Rails list. Okay. Okay, so let me consider my XY grid. Now, we note that firstly, when y is negative infinity, so it goes that way, something like that. When it goes to negative infinity, when x is negative infinity, when we go along the x-axis in the negative direction, it's going to go to minus. It's going to go to minus infinity. So it's gonna look. So it's going to go. It's going to come up like this, right? So it goes from negative infinity, right? As x goes to negative infinity. Now, we are told that the asymptote is x is equal to 0. If x is equal to 0, that's the y-axis, right? So it basically tends, the curve tends towards the x-axis. But we're then also told that the stationary point, first of all, minus a third is a maximum. So if minus a third is, say, here, it's basically going to look like it's going to have a top point. If I sketch it again, it's going to have a top point at a value of minus 4, and then it's going to go back down because it's going to tend towards 0. Okay. And yes, okay, so that's my first part of the graph. Then, because x is equal to 0, then it's going to come down like this. And we know it's going to come down like this. But we also know at x to the third, positive a third, at 4, it's a minimum. So it's going to come down at a minimum point here, and then we know that when x goes to infinity, so as we go along the right of the x-axis that way, then y shoots up to infinity as well. So then after it reaches this minimum, it shoots back up, and that's my graph. That is my graph. Okay, and it also makes sense because remember we also deduce there were no roots and there was no y-intercept, and we can see on our graph it doesn't cross any axis, so there are no roots or intercepts. So yes, so it satisfies Rails. So that therefore is what my graph looks like. Okay, cool. Okay, but I will say graph sketching is like this with unfamiliar functions. It's very difficult, especially for A level. Very, very difficult. I don't think I've ever seen an exam question where they've asked you to sketch like an unfamiliar graph, right? A graph that isn't sort of one of the standard graphs you need to learn, or a transformation, right? When you have to actually sketch something unfamiliar that isn't just a simple transformation. I've not seen a mask, okay? Maybe there will, I don't know, it's a final question, I don't know, but you can now sketch unfamiliar graphs, well, some unfamiliar graphs, by considering these 5 properties, okay, which I call Rails, okay. This is particularly useful if you're doing the MAT or STEP, really, but for A level, personally, I wouldn't try and go out your way to kind of sketch unfamiliar graphs if they're because they can be very difficult. And there's a lot to consider as well. But yes, that is how we approach graph sketching, and that's what the graph will look like. Cool. I mean, lastly, we could label our stationary point if we wanted to. So it'd be a third 4, and then this would be minus a third, minus 4, and that is a fully sketched graph. Okay, there we are. Okay, we're going to look at some exercises then. So hopefully you start to get a grasp. Really, if I would say the main thing I'd recommend to get out of this is the second derivative test. So you look at the sign. If it's negative, the second derivative, then it'd be a maximum. If it's a positive for the second derivative, then it'd be a minimum. And a point of inflection you need to consider if it's equal to 0. Okay, we're going to look at this exercise then, which actually isn't as bad as the other examples. But we're told that this curve is y is x, add 2 over x minus 3. We're given a sketch and we need to firstly find the coordinates of a and b. Now notice a and b are just the roots, okay? So the roots are when y is 0, or we just solve it equal to 0. So x add 2 over x minus 3 equals 0. And that is the roots, okay, if I solve this. How am I going to solve it? Well, I could just times everything by x, right? To get rid of the fraction. So then x squared add 2 minus 3x equals 0. Now I've got a quadratic, right? If I rearrange this ever so slightly, it's a quadratic I can solve. Right, can I factorize? So times to get 2, add to get minus 3. Yes, because if I take minus 2 and minus 1, those are my two factors. I add minus 3 times to get 2. So my factor x minus 2, x minus 1 equals 0. Therefore, my two values are x is 2, x is 1. Okay, so we can safely say then that a is x is 1 and b is when x is 2. But it's said to find the coordinates. Well, actually, y would equal 0 because it's on the x-axis. So therefore, a is x is 1, y is 0, and b is when x is 2, y is 0. And there we are. Part B then, it says to find the exact coordinates of C. Now what's special about C? It is a stationary point, right? As you can see, it's a minimum as well. More specifically, it's a minimum. So we need to differentiate and set to 0. I need to differentiate my my curve here. So y is x add 2 over x minus 3. Now, what's the problem? What's the problem here? That's going to cause me havoc if I try to differentiate. It's going to be the fraction here, right? I need to convert this 2 over x as an index. But that's going to be x add 2x to the minus 1 minus 3. And now I can differentiate. So, then if I do dy dx, if I differentiate, where x goes to 1, 2 to the 2x minus 1 goes to minus 2x to the minus 2. And then minus 3 goes to 0. Okay, so then I need to set this to 0, as it's a stationary point. So that means 1 minus 2x to the minus 2 equals 0. If I then, to help me out, just convert this back to a fraction, this minus 2. So 1 minus 2 over x squared equals 0. If I then times by x squared, so therefore x squared minus 2 equals 0. Therefore x squared is 2. So x is plus or minus root 2. So I've got two solutions, but the problem is, actually, no, we do know. Actually, I was going to say, do we know which value of x it could be? Because it obviously has to be a minimum. But I was going to say, maybe then you need a second derivative test to differentiate what type of stationary point we have. But look at the graph. We're given a graph and it has to be on the positive x-axis. So C has a positive x value. So at C, x is positive. So therefore, x is just positive root 2. And there we are. And so it then wants the coordinates of C. So it wants the y value as well. So we found the x value, but we know that y is x add 2 over x minus 3. So therefore the y value when x is root 2. The y, what was y again? Y was x plus 2 over x minus 3. Yes, okay. So then if we set x to be root 2, y would be, well, root 2, add 2 over root 2, minus 3, and my calculator gets me 2 root 2 minus 3. So therefore my point C, xy, where x is root 2, y is 2 root 2 minus 3. And there we are. Cool. They're cool. Okay, now with this question, we are told to find the maximum value and hence the range of values for the function f of x equal to this. So again, maximum value, it's kind of alluding to the idea of a maximum point. Okay, that's the whole idea about it. We will look at this in more detail at the end of this section. But the power of this, of stationary points, of minimum and maximum, the power of that allows us to optimize stuff. In other words, it allows us to find the maximum or minimum value of something. Okay, so optimization, to optimize to get the best or the worst result of something, which has a lot of applications, which we'll see in mechanics as well. But anyway, for now, we're asked to find the maximum value. That's alluding to maximum point. So, okay, we're going to need to differentiate. So f of x is 27 minus 2x to the 4. So then the first derivative is, well, 27 goes to 0, so it's just minus 8x cubed. Then the second derivative is going to be minus 8 times 3, which is minus 24x squared. Okay, so then my stationary point obviously occurs when the derivative is 0. So if we solve that then, the minus 8x cubed is 0, but therefore x has to be 0. So that's my point, x is 0. Okay. Okay, then if I substitute that into my second derivative, so at x is 0, then f dash dash of 0 is equal to, well, actually 0, right? So what that tells me is actually it could be a point of inflection. Now I say could be. It could also actually be a minimum or maximum, and probably it's going to give it away that it's going to be a maximum point. So the second derivative equal to 0 is an interesting case. It's usually it's going to hint towards a point of inflection, but it doesn't have to. It could be still either 3 points. What we're going to look at then is we're going to look at the sign. We're going to rule out if it's a point of inflection, okay? Because it hints towards a point of inflection. Spoiler alert, it won't be, but you'd think that, right? So if it's equal to 0, it could be a point of inflection. What we're going to do then is test around the second derivative. So I'm going to say f dash dash of x add 0.01, okay? If we then do that then, if we substitute 0.01 into here, so minus 24 of 0.01 to the power of squared, we get minus 0.024. Okay, that's negative, right? Also, if the second derivative is less than 0.01, we actually get the same answer. And you can see that because it's x squared. Remember, a square number, a positive and negative goes to the same thing. So what happens is there's no sign change around the point 0. So that means it cannot be a point of inflection. Not a point of inflection. So we rule that out. So it either has to be a minimum or maximum. Okay. And we don't know for sure because the second derivative at 0 is not positive or negative, it's equal to 0. We're in a bit of a pickle, right? We can't use our second derivative sign test here. We're going to go back to basics then. We're going to consider instead the sign of the first derivative, or the gradient, right? We're going to consider the gradient of the first derivative, the sign of the first derivative. So again, we know that f dash of 0 when x is 0, that equals 0. Okay, then again, if we then sort of test around, if we test around 0, so firstly let's consider before we reach 0. So let's say we subtract 0.01, a small number, right? Then if you put that into my gradient function, my f dash of x, which again I may remind you is minus 8x cubed, if I put minus 0.01, I get positive 0.00008, I think, right? I might be missing a 0, but the idea is it is a positive. Then if we go beyond 0, so if we add 0.01 after 0, well, actually the sign is the other way around. It's negative 0.00008. So what's happening here is the gradient before 0, it's going from positive to then a negative afterwards. So gradient, so f dash of x goes from positive to negative. So think about it then. That's saying that the gradient is positive to negative, or in other words, the curve is going upwards then downwards after the point. Okay, that obviously then is going to be a maximum. So therefore x is equal to 0 is a maximum. Cool. Okay, so then as a point net, well, the maximum value of the curve is going to be well, think about it. What's the curve going to look like? It's negative 2x to the 4, right? So remember, it's going to have like a M shape. Remember when we looked at cortex, it's going to have an M shape like this. So a maximum point is going to be sort of there, right? At the highest point. So the maximum value is going to be at the maximum at the point there, the maximum point. Okay, so then to find the maximum value, we're going to need to find the y value at the maximum. So x is 0 is the maximum. So therefore y at x then, when x is 0, y is going to be 27, take away 2x to the 4, at x is 0. That's just going to be 27, okay? So therefore maximum is the point x is 0, y is 27. So then therefore the maximum value of the function is the value at the maximum point. So it's going to be 27. Okay. And so that's it then. So the maximum value is 27. And then lastly, it's said to give, what was it, the range of values of the function. So the range of y values. Well, again, if you look at very briefly, it's a quartic. It's a negative quartic. So it's going to look something like this, right? So obviously it goes to negative infinity. So basically the range of values are sort of negative infinity as it keeps going down to a maximum point of 27. So my range of values is simply f of x has to be less than or equal to 27. Range of values is f of x is less than or equal to 27. Okay, and that's it. Cool. And again, that's sort of the idea of this sort of maximum minimum points. It allows us to find the maximum minimum values of something, which we can optimize all sorts of things in real life and stuff like that. Okay, I want to look at this example then. It's another graph sketching, and actually if people who paid attention when we did the cubic when I did the cubic equation video, this example came up, but we couldn't give the actual precise sketch for it. Okay, because we missed the detail. We missed the idea of stationary points. We now know that, so now we can give an accurate sketch of this curve. So what again we're going to consider rails. Okay. But actually, you might be thinking, well, isn't it just going to be a standard cubic? Okay, why do we need anything special for that? Well, okay, let's proceed. So remember, when we looked at sketching a cubic, firstly we saw what type of sign is it. We looked at the sign of x cubed. So the x cubed coefficient was just 1. Remember, x times x squared is x cubed. So the x cubed part of my curve is positive. It's positive 1. So it's going to have that sort of shape, okay? Then we looked at the roots, okay? And the roots are saying, well, we set obviously y would equal 0. So that means either x is 1 or x squared add x plus 2 equals 0. Now actually, again, if you did that in your calculator, you wouldn't get any proper roots, because you can check the discriminant, right? B squared minus 4ac will be 1 squared, which is 1, take away 4 lots of 1 lots of 2. That would be negative 7. 1 take away 8 is negative 7. That's negative, so no real roots. So actually that's telling me there's only one root here. So it only crosses the x-axis at 1, okay? So then you might be thinking, well, obviously we know x is 1 and it's a single root, so at 1 it would just pass through. And also the y-intercept when x is 0, then y, if I plug in x is 0 into here, I get y to be minus 1. So 0 minus 1, which is minus 1, times by 0 squared plus 0 plus 2. So times that by 2, I get minus 2. So it's going to cross down here at minus 2, right? So then you might be thinking, well, so then it passes through these 2 points, my x and the y axis here, and it has that sort of shape. But then you might be thinking, well, it might look something like this then, right? That is actually not true. Okay, that's not true. The graph doesn't look like that. It doesn't have a maximum or minimum. Obviously, if it looked like this, it would have a maximum point there and a minimum there. That's not actually the case. And stationary points is actually going to tell me the true answer, the true story behind what the curve actually looks like. So that's not how it goes. Obviously, we've got some key ingredients already. We know what the roots are. We know that x is 1. So roots, x is equal to 1. We know the y-intercept, that is what y is equal to minus 2. We also, well, we know there's no asymptotes, right? It's a cubic. There's no asymptotes. And then long-term behaviour, so when x goes to infinity or negative infinity, well, really, if x goes to infinity, y goes to infinity, and we can look at the shape here, right? The shape tells us when x goes to infinity, in the long term, y goes to infinity. And if x then goes to negative infinity as we go to the left, then x goes down to negative infinity as well. So it looks like a cubic, right? But what we're missing is stationary points. And this will tell me what the true sketch will look like. Okay, again, it's not going to look like if you have minus 2. Oh, if you have minus 2 and let's say 1, it is not going to look like this with 2 dips. It's not going to look like that, okay? Let's show what it's going to look like. Well, let's compute the stationary point. So we know that y is equal to x minus 1, x squared add x plus 2. Well, firstly, if we are going to differentiate, we need to expand those brackets, right? So, if we expand these brackets, well, firstly, well, it's going to be x cubed add x squared add 2x, take away x squared, take away x, take away 2. And we can simplify, so we're going to get x cubed add x squared, take away x squared, that will go away. 2x take away x goes to plus x minus 2. That's my simplified y value, that's my function there. So then dy dx, if I differentiate this, I get 3x squared add 1. Now, if we were to set that equal to 0, well, actually, that's telling me that x squared would be minus a third. We can't square root a negative, so there's no solutions. So there are no stationary points. Right. But, if we then do the second derivative, that'd be 6x. Well, actually, if we set that equal to 0, x is 0. That is actually then going to be a candidate for a point of inflection. Now, it can, at this point, because it's not a stationary point, it cannot be a minimum or maximum. But actually, a point of inflection doesn't have to be a stationary point. You can have a point of inflection even though the first derivative might not be 0. It can still be a point of inflection. A point of inflection is actually independent to, really, you should think of it as being independent to the first derivative, really. A point of inflection doesn't have to be a stationary point, okay? It doesn't have to be the first derivative to be 0, but a point of inflection does need the second derivative to be 0, okay? So we might have a point of inflection, and again, remember, a point of inflection might look like it levels off and then goes up like this. It might be a point of inflection there, which makes sense because it's a cubic graph, right? Anyway, so x is 0. What we're then going to do, we need to verify it's a point of inflection, because remember, one criteria is the second derivative has to be 0. That's not all. We then need to consider the sign around the point. So then what I'm going to do is, let's say, let x to be, well, not 0, but take away, let's say 0.01. Let's go a bit beyond, let's go a bit before 0. Then my second derivative, which is 6x, that's going to be minus 0.06, and that's going to be negative. Then if x is, let's say, positive 0.01, so a bit after 0, then the second derivative is actually positive 0.06, and that's positive. So there is a sign change. So that's the second piece of the puzzle. There is a sign change in the second derivative, so that means x is 0 is a point of inflection. So remember, a point of inflection is when the second derivative is 0 and there is a sign change around the second derivative, in this case here. Nothing to do with the first derivative, but a point of inflection can still be a stationary point, but it doesn't have to be. It's all to do with the second derivative, okay? And now we actually shown there is a stationary point at 0. So then if I were to compute the point then at 0, so if x is 0, then y would be, y is x cubed at x minus 2, so that'd be 0 cubed at 0, that'd be minus 2, right? If x is 0, y is minus 2. So therefore 0 minus 2 is a point of inflection. Oh. So I can add that on, if I go up here, 0 minus 2 is a point of inflection. So it's going to have that leveling off sort of idea, right? Now we've got all the ingredients then, so you can do an accurate sketch. So okay, I'm going to get rid of this now. So okay, we have x and y. So firstly, our root is x is 1. We also know the y-intercept is at minus 2. Now that's also the stationary point. So if I mark minus 2, say here, there we are. Okay. We also know there's no asymptotes. We know the long-term behaviour. It's going to look like this shape, right? Still going to look something like this. But so it's going to come from negative infinity. It's going to come down here. Then instead of it being like two humps, right, it's actually just going to be a point of inflection. So what's going to happen is it's going to level off at -2, then it's going to shoot back up to 1, and that is what the curve is looking like. It will not look like this, where with 2 humps, a minimum maximum. That is not what the curve looks like. It is this instead, with no humps, just a point of inflection. Okay, there we are. Okay, so now we're in a position where again we can properly sketch graphs now. Okay, because of the added ingredient of stationary points to help us investigate how the curve behaves, right? Certain key points or features of the curve. Okay, so yeah, it's quite cool. So we can go back to this was again from chapter 4. We couldn't give the accurate sketch because of this idea of a point of inflection, right? But now we can sketch it quite accurately. So there we are. Okay, so we got some exam questions here, and actually I think you'll notice that compared to how the textbook, which is what I've gone through so far, how the textbook asks questions and the exam questions are a bit different, and I do think the exam questions are a bit nicer compared to some of the stuff that we've looked at. Okay, okay, so we're going to look at this example first. We're told that y is x squared minus 2x minus 24 root x. It's asking us firstly to find dy dx. Well, before I do that, well, we need every x as just powers, but I have a root x here. That needs to be dealt with. I can then simplify that to x squared minus 2x minus 24x to the half, right? Now I can differentiate this. So then if I differentiate, that would be 2x. Take away 2. Take away, now 24 times a half is minus 12. X to the minus a half, right? If I subtract 1 from the power, half minus 1 is minus a half. There we are. Then the second derivative, if I differentiate that again, I will get, if I differentiate this, I will get 2. Then the 2 goes away to 0. Then minus 12x to the minus a half, that would be plus 6, x to the minus 3 halves. And there we are. Cool. Then part B then ask us to verify that the curve has a stationary point when x is 4. Now, remember, stationary point is where the derivative is equal to 0. Now, quite interestingly, that they're not at this is an exam technique prompt here, but it says verify. What that means is, and they're giving us a solution. So they told us x is 4. When it says verify, it means you need to show, basically by substituting it in, almost like just checking the answer. It basically means check it's correct. We don't need to show to get x is 4. We need to just show that x is 4, right? We need to show check it's the right answer. Well, again, we need to substitute x is 4 into my derivative then, right? Then when x is 4, my dy dx, which is this expression here, that's going to be 2 times 4 minus 2 minus 12 of 4 to the minus a half. Then I hopefully should get 0 if I put that in a calculator. Yes, 0. So therefore it has to be a stationary point. Okay, so x is 4 is a stationary point. Or I should say, there's a stationary point at x is 4. There's a stationary point at x is 4. And there we are. So yeah, so again, exam tip, if it says verify, usually it gives you an answer. You need to check that answer is indeed the answer. So you need to, in this case, check it's a stationary point by making sure the derivative is 0 when you plug that in. Part C, we need to determine the nature. So again, that exam language. The nature of the stationary point means, is it a minimum, maximum, or point of inflection? It's a max, a min, or a point of inflection. And so how are we going to do that? we're going to use the second derivative. So we know that x is 4, right? That's my stationary point. So then we're going to substitute that into the second derivative. So as x is 4, then the second derivative, if we substitute that into here, that's going to be 2 add 6 lots of 4 of minus 3 over 2. If we put that in the calculator, we get 11 over 4, or 2.75. And that's positive. So then you need to remember, if it's positive, the second derivative, it has to be a minimum. So as d squared y dx squared is positive, it is a local maximum. Minimum. Okay. That's it. Okay, that's it. Okay, so I think this question summarises what we've done quite nicely, quite succinctly. But yeah, there we are. Now we are told this exam question here, and we're told in here the curve C has the equation y is f of x. Well, f of x is this. So okay, we know that f of x is ax cubed. Add 15x squared minus 39x add b. We are given now that the point 210 lies on C and the gradient of the curve at 210 is minus 3. So this is going to be simultaneous equations. We've got two pieces of information and two variables, two unknowns, A and B. Well, firstly, let's work the first point. We're told the point 210 lies on the curve. So what that means is, if it lies on the curve, that means 210 satisfies the equation, right? So if I substitute this 210 into f of x, therefore we can say f of 2, so f of x, if x is 2, f of 2, that has to equal 10. If I substitute 2 into here, then I'm going to get a lots of 2 cubed, add 15 lots of 2 squared, minus 39 lots of 2, add b. If I then simplify it, well, 2 cubed is 8, so I'm going to get 8x. And then 15 of 2 squared minus 39 lots of 2, that's minus 18. Then we add b. And we're told that has to equal 10. So therefore, 8a add b, if I move the 18 to the other side, I get 28. So that's my first equation. Now, I'm also then told that the gradient of the curve at that point is minus 3. So remember, the gradient is f dash of x, right, the derivative. So if the gradient at 210 is minus 3, that means f dash of x is minus 3, particularly when x is at the point 210, right? So at the point 210, the gradient is minus 3. So that means f dash of 2 for x, right? If x is 2, then the gradient is minus 3. So I need to compute the derivative then, right? If I have f of x, I need to find f dash of x by differentiating, right? So ax cubed will go to 3ax squared, then 15x squared will go to 30x, minus 39x will go to minus 39, and b will just go to 0, as b is just a number, right? It's not an x, it's just a number. It's just an unknown number, so that goes to 0. So then we're told f dash of 2 is equal to minus 3, right? That's what it's telling me. The gradient at the point is minus 3, so that means that f dash of 2, if I substitute 2 into here, it's going to be 3a lots of 2 squared, add 30 lots of 2 minus 39. So if I simplify that, well, 2 squared is 4, 4 times 3 is 12. So 12a, then 30 times 2 is 60, take away 39 is 21. Okay, no, sorry, yes, plus 21, okay, so there we are. So we simplified it, this expression, we're told it has to equal -3. So the gradient is -3. So that's my equation. So if I subtract 21 to both sides, I get 12a is -24. That means a is going to be -2. If I divide 24 by 12, I get -2. So that means I've got my a value. I can then sub that into here. So sub a into 8a add b is 28 to get b. So therefore 8 lots of -2 add b is 28. So therefore b, well, if I simplify it, well, 8 times -2 is -16. Add b is 28. So b, if I add 16, so 28 add 16 is 44. So therefore, that's my a and my b value. Cool. That's part A done. Find that value of a and b. So show that a is -2. That's what we did, right? A is -2. Cool. We now need to show that hence means you need to use your previous working or your previous answer. So basically means we need to use the value of a and b. Okay, we need to show that C, the curve, has no stationary points. So in other words, there are no points where dy dx is equal to 0. Right. So we know what a and b is now. We can bring that into my f of x. Right. So if I do it up here. So f of x then, now ax cubed, well a is -2, so -2x cubed, add 15x squared, minus 39x, and then b was 44, so add 44. Okay, that's my function now, with my a and b values filled in. Now, I need to show there's no stationary points, so I need to consider the derivative, right? Actually, we did the derivative, actually. I'll do it again though. So f dash of x, if I differentiate this now very quickly, that'd be -6x squared, add 30x minus 39. So then if it has no stationary points, well, let's consider what happens when this is set to 0. And hopefully you recognise we're going to get a quadratic equation right here. How do we check? If there's no stationary points, that has to mean there are no solutions, right, really, to this. How can we check, if we would think back, how can we check if a quadratic has any equations or not? The discriminant, right? Let's consider b squared minus 4ac. If we work this out, that's going to be, well, 30 squared, take away 4 lots of -6 of minus 39. So if we work that out then, that would get me minus 36. But that's a negative. So again, if the discriminant is negative, there are no real solutions here to that equation. So therefore, there are no solutions really to this equation, to the just setting it to 0. That means the derivative cannot be 0. So f dash of x cannot be 0, therefore no stationary points. And there we are. Cool. Okay, we're going to finish up with this final exam question, which I think is interesting. It was towards the end of an AS paper. It's like a puzzle, really, I'll describe it. But let's have a look. We're told the curve has equation y is g of x. Given that g of x is a cubic expression for which the coefficient of x cubed is equal to the coefficient of x. The curve passes through the origin. Now the origin is going to be 0, 0. And the curve has a stationary point at 2, 9. We need to find g of x. We need to find the expression for g of x. Now, we're told that g of x is a cubic. We can give so we can generalize, right? So remember, a cubic expression, g of x, a general cubic is ax cubed plus bx squared add cx add d, right? So really what I need to do is find my missing coefficients a, b, c, d. Right, so what we're first told is the coefficient of x cubed is equal to the coefficient of x. That means that the coefficient of x cubed, which is a, and the coefficient of x, which is c, have to be the same. So A equals C. So then I can simplify this to say g of x is ax cubed add bx squared add ax add d. Okay, I'll get rid of the c. I don't need the c. Now, the next bit of information I'm told is the curve passes through the origin. I can just substitute that in then, okay? You might be able to just tell me immediately that d has to be 0 and you'd be right. But if I was to substitute that in, so 0, 0. So I'm going to sub 0, 0 in. Which means that g of 0 has to equal, if I put in 0 for x here, well, that'd be a lots of 0 cubed, add b lots of 0 squared, add a lots of 0, add d. That will go to 0 apart from d. So that has to be 0 because obviously it's the origin. So the y would be 0, g of x would be 0. So then I can I now know that d is 0. I can then once more complete my expression, so that it's going to be ax cubed add bx squared add ax, and then that's it because d is now 0. Now I'm then told that g of x has a stationary point at 2, 9. So that means that g dash of x, the derivative has to be 0. Now if I then compute the derivative of this expression, if I differentiate, I will get 3ax squared add 2bx add a. I am then told that 2, 9 is a stationary point. That means x is 2. That is what I'm going to substitute in. So at x is 2, g dash of x is equal to 0, right? 2 is a stationary point for x. So therefore g dash of 2, if I plug in x is 2 into here, that'd be 3a of 2 squared, a 2b of x of 2 add a. If I then simplify that, well, 2 squared is 4, 4 times 3 is 12a, then 2b times 2 is 4b, add a. Now 12a add a is 13a, add 4b. And because then the derivative is a stationary point, so the derivative is equal to 0. So therefore I can say 13a add 4b is equal to 0. Right. Well, that's really it. What other information do I have? And this is where you really need to pay attention, right, to all the key details of what the question's saying. I need another equation, right, to find a and b. Notice here has a stationary point at 2, 9. Not only is it a stationary point, more simply, 2, 9 is just a point. So that's a point I could substitute into my g of x, my curve. So there we are. So then if I sub 2, 9 into g of x into here, therefore g of 2 equals 9. So therefore if I plug in 2 into g of x, that'd be a lots of 2 cubed, add b lots of 2 squared, add ax, a lots of 2, that would go to 2 cubed is 8, 8a, add 4b, add 2a, and that goes to 10a, add 4b, and we're told it has to equal 9. Well, there we are, we've got simultaneous equations, right? We've got this equation and this equation, right? So if I jot that down somewhere, so 13a plus 4b equals 0, that's going to be equation 1, then 10a add 4b equals 9. That's equation 2. These are simultaneous equations, right? Now I can solve for a and b. Now you can solve them however you want. You might even be able to get away with just putting it in the calculator. I would always be very wary of stuff like that. You never know what the mark scheme will say, what you get marked for method marks. So let's just solve normally without the calculator doing all of it for us. Well, I notice very simply I can just take both equations away because I have 4b on both equations. I can take that away to get rid of b. So if I do the first one, take away the second one, 13a take away 10a, it's going to be 3a, then 4b take away 4b, 0, then 0 minus 9 is minus 9. Therefore a is minus 3 if I divide by 3. So that's my a value. Therefore b, if I substitute that a back into either equation, let's substitute it into the second one. So 10a add 4b equals 9 would get me 10 lots of minus 3 add 4b equals 9. So minus 30 add 4b is 9. If I add 30 to both sides, I get 4b is 39. So therefore b, if I divide 30 is 39 over 4, right? And that is my value for b, 39 over 4. Okay, so I found all my coefficients now for g of x. So therefore g of x then, so if I remind you, g of x was ax cubed, add bx squared, add ax. Now I know a is minus 3, so it's going to be minus 3x cubed, and b is 39 over 4, x squared, minus 3x, and that is g of x, okay, with all the coefficients determined. And there we are, that is my complete function. There we are. Okay, so see how it's kind of like a puzzle. Lots of information, you have to find equations for to find missing values. But there we are. That's the hard bit done. 7 marks. There we are. Now we need to prove that the stationary point is a maximum. So obviously we're told 2, 9 is a stationary point. What we need to prove is that it's a maximum. Okay. So how are we going to do that? Well, we can consider the second derivative, right? So then if we differentiate g dash of x, that would be if we differentiate g dash if we differentiate g of x, get g dash of x. That's going to be, if we differentiate this, well, minus 3x cubed will be minus 9x squared. Then 39 over 4 times 2 will be 39 over 2x minus 3. And then if I differentiate again to get the second derivative, that would be minus 18x, add 39 over 2. Now, we need to show that we need to substitute 2, 7 in, right? We need to show that this stationary point 2, 7 is a maximum. So we need to consider what happens at x is 2. When x is 2, then g dash, then the second derivative of x, that's g dash dash of 2. If I substitute x is 2 into here, I get minus 18 lots of 2, add 39 over 2, and that will get me minus 16.5, and that is a negative. So therefore g dash dash of x is negative, which means it has to be a maximum. And that is what the question asked us to prove. And there we are. Okay, cool. So that's it, right? So yes, so we looked at how we can, well, we looked at what is a maximum, minimum and point of inflection, and how we can use the second derivative or maybe even the first derivative by looking at the change in sign to work out a stationary point, which is a maximum, minimum or a point of inflection, right? That's the key idea, right? So we can use the second derivative or otherwise to work those points out. Okay, so that's it for this section. I'll see you next time.